So far we have seen that when you have a nonlinear circuit and you have a certain operating point already computed, when the values of the input change or when there is some change in the stimulus to the circuit, you can represent all quantities as increments over the operating point. And if you do this and neglect the higher order terms in the Taylor series of the nonlinearities, the relationship between the incremental quantities alone, okay, this does not apply to the operating point, but only for the incremental quantities, the relationship will be linear. Okay. So, for instance, for this particular circuit, assuming that the diode current is a nonlinearity f of the diode voltage, then the incremental voltages Vs and Vd have this relationship. Okay. Now, this Vd is the variable. The incremental diode voltage can be obtained as Vd equals Vs 1 by f prime at Vd 0 divided by R plus 1 by f prime at Vd 0. Okay. There is a reason I write it in this form. This form looks very similar to that of a voltage divider. The voltage across the diode is the source voltage times some number divided by the resistance plus some other number. Okay. And it is very clear that this number has dimensions of resistance also, because f of Vd is the diode current. Okay. Now, f prime is nothing but the derivative of Id with respect to Vd, which has dimensions of conductance, and the reciprocal of this is a resistance. Okay. So, essentially it appears that the incremental quantities can be found from this circuit. Okay. I have not derived this, I am just putting down this circuit. So, for instance, if I had a linear circuit where the input source is Vs and there is a resistive divider, this resistance is R, exactly the same as here, and this resistance is 1 by f prime of the diode characteristic calculated at the operating point, you will get the same solution, right, because clearly the voltage that you see between these two terminals is equal to that. This you know from the resistive divider formula. Okay. So, what I want to show is that this is not a coincidence. It is not that for this particular simple circuit this happened to be the case. Now, it turns out that in every circuit the nonlinear element can be replaced by some linear equivalent. Okay. Now, this is not very surprising. We replace the nonlinear characteristics by a straight line around the operating point. Okay. So, the nonlinear element can be itself replaced by a linear element, and this is easier. Okay. So, while this business of expanding the nonlinearity in Taylor series and neglecting higher order terms, this is easy, we still do not want to set up the equations every time and then go about this business of neglecting higher order terms. Okay. We want an even more straightforward way of arriving at the solution for the incremental quantities, and that we do by considering the incremental equivalent for every element. Okay. So, the reason I showed the equations is to show that it is a general method. Now, what I will show is that every nonlinear element can be replaced by a linear equivalent, and the resulting equations will of course be the same as what you would get if you expanded every nonlinearity in a Taylor series and neglected higher order terms. Okay. So, instead of considering the whole circuit, what we can do is to just consider a single element. Okay. So, we have a voltage V and a current I, and we know that I is nonlinearly related to V. Okay. By the way, we could also express V as the voltage as some function of the current. Okay. So, I just use this formulation most of the time, but this is perfectly valid, and these are like equivalent statements of Ohm's law. Okay. You could write I equals V times the conductance, or V equals I times the resistance. Okay. So, this is for a linear element and this is for a nonlinear element. Now, let us say the nonlinear element is in some operating point condition. Okay. We have V0 and a current I0 flowing through it. Obviously, I0 equals f of V0. These two quantities satisfy this equation. Okay. And let us call this the operating point. Now, any other value of V can be thought of as the operating point plus an increment, and any other value of y can be thought of as the operating point plus an increment. So, now this is V naught plus lowercase v, this is I naught plus lowercase I. Okay. And these quantities also obviously have to satisfy the constraint imposed by the element, which is its nonlinear characteristic. Okay. Now, I expand this in a Taylor series about the operating point. So, I get f of V naught plus f prime calculated at V naught times V plus higher order terms. Okay. Again, if this deviation V, the increment V is small enough, I can neglect all the higher order terms, and also I already know that I naught is f of V naught. So, this goes with that. So, the incremental current I is nothing but the derivative of the characteristic at the operating point times the incremental voltage V. Okay. So, as far as the increments are concerned, the current is proportional to voltage, which means that it behaves like a resistor. Okay. So, this is only for increments. The incremental voltage V and the incremental current I are related by this expression. Now, there is something dependent on the operating point here, that is the value of the resistance itself. Okay. So, let me denote the resistance by lowercase r. This is just to indicate that it is the incremental resistance, and that will be equal to the reciprocal of the slope at V naught. Okay. Now, it is the reciprocal of the slope because the function gives you a current as a function of voltage. Okay. Or the incremental conductance G is f prime at the operating point. Okay. So, every two terminal nonlinear element is a resistor for incremental quantities provided the increment is small. Okay. So, it is extremely important to remember that this equivalence is only for the increments, and the value of the resistor depends on the operating point. Okay. And this is called the incremental resistance, and because it is valid only for small increments, it is called the small signal incremental resistance, or similarly the quantity G, which is f prime, this is known as the incremental conductance. Okay. If the nonlinearity were represented like this, voltage as a function of current, then the incremental resistance would be the slope of h calculated at the operating point. This is whatever the operating point is. Okay. and the incremental conductance would be the reciprocal of this one. Okay. So, every nonlinear element can be approximated by a linear element. Now, you see why this method is easier. We do not even need to write the nonlinear equations of the original circuit. You have to do it for calculating the operating point, but that point onwards for increments, all you have to do is look at each element and replace it by its incremental equivalent. Okay. So, what do I do? My original problem was to calculate the solution to this. Okay. Where this V naught comes from the operating point. That is, I have already calculated the solution for V naught. Okay. I have solved for this, and of course, I can also include the currents here. So, this is I naught plus I, and this is I naught. So, one thing I could do, of course, is go through the process of solving the nonlinear equation again, but what I do instead is make a new circuit which consists only of incremental quantities. So, I have this incremental Vs here, and I have R. I will come to the incremental equivalent of a linear element. The diode I replace by its incremental equivalent at the operating point. Okay. So, it is extremely important to remember that the incremental resistance or incremental equivalent in general depends on the operating point. Okay. So, if you today calculated the incremental equivalent of a diode at an operating point current of 1 milliamp, and tomorrow you have a different operating point current, let us say 10 milliamps, the incremental equivalent will be different. Okay. So, that you have to keep in mind. So, this will be the incremental diode voltage, and this will be the incremental current in the circuit. Okay. So, it is very easy. So, if you want the incremental diode voltage, it will come from the voltage divider formula, and if you want the incremental current, it will come from Ohm's law, and so on. This is of course a very simple circuit, but regardless of the number of nonlinear elements you have, you can do this for any circuit. Okay. So, every nonlinear element has to be replaced by its incremental equivalent at its operating point. Okay. So, you could have two diodes in the circuit with different operating points, that is, one could be having an operating point current of 1 milliamp, the other one could have 10 milliamps, they will have different equivalent resistances in general. Okay. And this circuit, which relates only the incremental quantities and is linear, this is known as the small signal incremental equivalent circuit. So, sometimes it is called the small signal equivalent, sometimes the incremental equivalent, and so on. You have to remember that this is valid only for increments about the operating point, and also it is valid only when the increments are sufficiently small, so that you can neglect the higher order terms. Okay. Now, what is sufficiently small is very dependent on the nonlinear element you have, and so on. The only definition I can give is that it should be small enough, so that second order and higher order terms should be negligible. Okay. And also, when you say negligible, you have to specify some accuracy. So, depending on the accuracy of the solution you want, you can restrict the size of the increment. Okay.